Hello, everyone. Thanks for joining this webinar. I know this is not our regular time, but thanks for joining. So today we have a very exciting presentation. So before I get into today's presentation, I just want to mention about this webinar series. I think many of you might have attended the previous webinars, so this is kind of a repetition for them, but for others who are new, they could know that this is weekly webinar series. So we generally have on Fridays, 9 a.m. Chicago time. This is on broad topic of geoenvironmental engineering, polluted land, waste management, sustainability, and resiliency. So it covers a lot of different topics, and it's mainly meant for graduate students, postdocs, young faculty in geotechnical engineering, environmental engineering, and related fields. So, these webinar series have been going on since January, mid-January this year. So the aim of these webinars is to make attendees understand various geoenvironmental problems and make them understand, ongoing research projects and research methods that are being adopted, and also, to develop research ideas that can be pursued for master's thesis or PhD thesis, or for young faculty if they're looking for a new area of research to pursue, to help them out in that regard, and also to create a network of geoenvironmental engineering researchers, just making these connections possible. I think, a lot of attendees have already started connecting to the speakers, connecting to other, participants. So that's a good outcome of this webinar series. So this is our schedule. We have scheduled webinars until the end of this year. Today we have an excellent presentation, and next week we're going to have a presentation on geophysical methods to assess landfills and site contamination. So that would be kind of a very interesting presentation that you can attend. And you can see other presentations are also, very interesting on, emerging topics. So, we have been having these webinars for a while, and all the webinars have been recorded with the consent of the speakers. And if you are interested in any webinar that was held in the past and you could not attend, feel free to go to this YouTube channel and view those webinars. So for today's webinar, these are the numbers from yesterday, but as I speak today, I have 520 registrants for this webinar. So I would recommend you to mute your mic and switch off your video. Type your questions in the chat box at any time during the presentation. So our presenter will answer the questions at the end. Again, thanks again for joining this webinar in spite of being at a different time. I want to introduce very briefly today's webinar speaker. Today's presenter is Dr. Alessandra Polettini. Dr. Polettini is a full professor in the Department of Civil and Environmental Engineering of the University of Rome, SAPIENZA. She is also the chair of the undergraduate and master's program in environmental engineering. And she gives the lectures on sanitary and environmental engineering, solid waste treatment for undergraduate and graduate students. She is a member of School of Advanced Studies of the University of Rome, La Sapienza. So her research interests are very broad and very interesting. They include the treatment and recycling of residues from thermal waste treatment, anaerobic digestion of organic waste, degradability of bioplastics, accelerated carbonation of alkaline residues, environmental behavior of waste materials, and treatment of contaminated jet sediments. So as you see, many of these issues are of concern to geoenvironmental professionals. So these are all very important and emerging topics. So she has co-authored over 150 scientific papers that have been published in international journals and conference proceedings. So I've been following Professor Alessandra's work for a long time, and so I read her papers. but I got a chance to meet her several years ago. Alessandra, if you remember this picture, this was like a, I don't know when it was, several years ago. I happened to be in Rome and visited her university, gave a presentation, and I had 2 days of good time in Rome. I still have vivid memories of those things. So personally, I found Alessandra to be very kind person and very smart person in terms of her research. So I'm glad she accepted my invitation to give a webinar as a part of this webinar series. So with that introduction, I will stop sharing and I will request Professor Alessandra to share her screen and start her presentation. Thank you so much again, Alessandra, for your taking time and giving this presentation.
Yeah, thank you very much for the introduction. It was really nice to see that picture from, 6-7 years ago. Very hot weather in Rome at that time, the middle of summer. Anyway, I'm sharing the screen and I hope this is visible.
Yeah, it's good.
Okay. And yes, I'm glad to be here to present some principle behind the work we are conducting on the organic waste biorefineries. And actually, it was not easy to arrange the presentation because with such a big audience from different sources, from different areas, it's not so easy to understand what the background is of the attendance. So I hope this is a good mixture of general overview and also provide some details on the topic. So again, I'm focusing on biorefineries applied to organic waste. And just a background about what the driving forces are for the implementation of biorefineries. So we have a number of issues that are related to this kind of topic. We have economic issues related to the limited availability of natural resources, for example, fossil fuels, and other kinds of natural materials. So we have the issue of fluctuating market prices, which can make environmental resources not very attractive from the economic point of view. We, of course, are also seeing a growing demand for energy, for fuels, for a range of materials, for chemicals, due to the growing degree of industrialization in many parts of the world. And also we have many countries which are dependent on important resources. Then we have a number of environmental and technical issues, for example, related to the mitigation of climate change effects, to the rational uses of natural resources, and also to the technological advances that have been recently made to exploit different materials, along with processes that ensure very high environmental sustainability nowadays. Then we have also political, social drivers, for example, the emergence of new policies, new regulations. We are experiencing day by day new regulation, for example, in the European Union, incentives to the boosting new processes, sustainable processes for example, recycling of materials, and also restrictions for the use of conventional natural resources. Then we have the competition of between industries, and also the tendency to build an integrated development between agriculture and industry. So these are the main drivers of the development of the biorefinery concept. And also, if we have a look at the use of primary energy in the world, what we can see is we are still relying on conventional energy sources. This is the percentage of the primary energy that is used on the basis of the energy sources. So basically, we are still relying on coal, very much on oil and natural gas, and not so much on other renewable sources. So you can see also that the situation has not dramatically changed in, let's say, 20 years, which is rather surprising. Then when we look at the situation in Europe, this is a bit different. Europe is now trying to boost the use of renewable sources. So all countries belonging to Europe have set different targets in terms of the share of renewable energy with respect to the total energy that is used by the different countries. So we can see that we have targets to be met last year, and most of the countries are almost there, or have, for example, Sweden or Denmark or Finland, they have even exceeded the set target. So it's a bit different situation with respect to the rest of the world. Another driving force is related to the reduction of greenhouse gases emissions to tackle the climate change effect, which is, I mean, a very modern and very important issue nowadays. So this is representation of how different strategies to reduce greenhouse gases emission can the contribution that they can have. So this baseline is basically the trend in increasing increase of the amount of CO2 that is emitted over time, considering the current trend that we observe nowadays. So if we're still keeping with the emissions at the current level, we are going to, I mean, rise in terms of total CO2 emissions. So how to cut these emissions, how to go down with the increasing trend of CO2 emissions. This is basically the target by 2050. So, of course, we can tackle the issue of climate change by integrating different technologies. You see here carbon capture and storage, the use of renewables, also the nuclear energy, and some other contributions. And of course, you see that the biorefinery concept may be involved in these, probably these two types of strategies. So carbon capture and storage and use of renewable materials. Another issue is the quality of the products that we get from utilization of residual materials. So we can say that the products that we may generate in general have different economic value. So the lowest level, the lowest value is represented by thermal and electric energy. Then we have higher value for biofuels, for example, biomethane, bioethanol, and so on. Then we have increasing the value, bioplastics or other biopolymers, animal feed and food ingredients, and at the top of this pyramid, we have refined chemical products. So when it comes to the biorefinery concept, what do we mean with a biorefinery? So there are several definitions of biorefineries. So basically, I'm reporting here the one from the International Environmental Agency. According to this definition, a biorefinery is a way to sustainably process biomass to derive a number of marketable products and energy through a combination of different biochemical and chemical or thermochemical processes. And these outputs may include liquid or gaseous biofuels, biopolymers or bioplastic materials, enzymes, food ingredients and animal feed, and refined chemicals, for example, organic acids, diols, pharmaceuticals, and so on. We may have a very broad range of potential products. So we have an input, a feedstock to the biorefinery, and then we produce a range of big range of valuable products. What kind of principles are behind the biorefinery concept? One of is the cascading principle. So cascading means that we are combining different processes, as I mentioned before, biological, chemical or thermal processes to produce a mixture of different bioproducts. So biofuels, biomolecules, and the integration of all these processes and technologies is aimed to maximizing the production yields and the incomes. And of course, this also implies a good quality of the products that we generate. In terms of the approach in the cascading principle, we can have two different, let's say, viewpoints. We may have a direct, or what we call the traditional cascading approach, where we have the biomass or even bio-waste. We produce first biomaterials, bioproducts, and then as a second stage, bioenergy. Or we may have an inverse cascading approach, where we have first the generation of bioenergy and then the generation of added value products. And as far as I know, now the inverse cascading approach is becoming more popular and more studied than the traditional one. Of course, the choice of either cascading approach depends on a number of factors. First of all, the feasibility, the technical feasibility, and also the economic sustainability of the processes that we have in mind to implement one of these two approaches. Local needs and also constraints, existing constraints, and also strategic priorities for the area that we consider, and other boundary conditions, for example, the availability of natural resources that we want to replace, the market conditions, energy supply policies, the strategies in energy generation in a given area. So, number of factors that, of course, need to be considered as a whole. Options for biorefineries. So, on one side, we may have dedicated energy crops, and on the other side, we may have a range of organic wastes, for example, the organic fraction of municipal solid waste, farm wastes, or agro-industrial residues. So, which of the options should we pursue, or should we consider as the most valuable one? What I believe is that, of course, now we are often talking about the food versus energy dilemma. So if we grow dedicated crops to be used later on for energy generation purposes or to produce. Sorry, there's a microphone on. If we grow dedicated crops for energy generation purposes or produce other valuable materials, of course, we use up parts of land that should be used for food production. So this is becoming a very important, a very critical issue, for example, in countries where, I mean, there is a scarcity of resources, of food resources. So, of course, we are not considering these as a viable options, at least on a large scale, while we believe that organic wastes are, I mean, low value materials in general that can be used, that must be treated and can be used and exploited to produce a range of valuable products. What types of residual biomasses or residual materials we may think of using in a biorefinery? So we have a lot of options. These are just a few examples. As I mentioned, we may have municipal solid waste, actually the organic fraction of municipal solid waste, sewage sludge. We may have forestry residues or agro-industrial and food processing wastes, fermentation waste, animal processing waste, marine processing waste, or agricultural residues and biodiesel production waste. So a big range of potential feedstocks that in principle are all suitable for the implementation of the biorefinery concept. Of course, depending on the quality of the material that we intend to feed to a biorefinery, we also expect a different quality of the products that we get. So in case of more pure, let's say, materials, for example, agro-industrial food processing residues or forestry residues, we may expect to be able to produce a wider range of products, even those of higher quality, while for municipal waste and sewage sludge, which are more, I mean, contaminated by undesired components, of course, probably we will be able to produce just a shorter range of products with lower quality in general. A few words about the analysis of the context. These are data that refer to Europe. Not very recent, actually, but I couldn't find more recent reliable data, but more or less, I mean, the order of magnitude has not changed so much. So in Europe, we have something like 120, 140 million tons of bio-waste generated per year. And of this amount, about 90 million tons per year are made of food waste, and the other 30 or 50 million tons per year are or include food processing waste. So these are both, I mean, potentially suitable feedstock to be used in biorefineries, but of course we also have to tackle with a very important issue, which is the overproduction of food and the issue of food waste and food loss, which is taking a big part of the bio-waste generation all over the world. When we consider the exploitation of organic waste, these are data again for Europe, we see that in general, the organic fraction of municipal waste is something like 35–40% of the overall amount of municipal waste produced. And according to this ECN data, ECN is a Dutch research center, just about a third of the organic waste is actually exploited, used in some different applications. The rest, almost 70%, is really wasted, so it's not used properly. So, of course, we have still room for improvement in the, I mean, recycling rate for this material, or for this waste. The main use of bio-waste in Europe is related to the composting. So production of compost through aerobic degradation of the organic fraction of the waste, and also to anaerobic treatment aimed at biogas production. And of course, in this case, we have the digest that can be then treated and again used for agricultural purposes. These are traditional uses, and I mean, take most of the amount of organic waste that is now managed in Europe. World data about what I was mentioning before, food loss and food waste. Usually food loss refers to the amount of food that is wasted at the stage of production. And food waste is what is wasted at the consumer stage, so it is discarded during consumption. So you see here that we have very big circles. These are data in million tons. So you see here how much waste is lost, or I mean, is wasted all over the world every year. Some data again for the world about the production of agricultural residues. I took this data from a study that you see cited here. Different crops that are I mean, grown in different parts of the world. Of course, each part of the world, each area, geographical area has its own specificity. And of course, we have different residues being produced from different crops that are grown. So you see here the potential in, again, in million tons per year for the exploitation of different residues from different crops. Generations, what we call generations of biomass. We have different generations in terms of, let's say, complexity of the processes that we can apply to treat biomass, and in terms of the products that we can derive from the exploitation of this kind of biomass. So what we call the first generation biomass is or involves very simple processes, typically, for example, agricultural crops that contain easily extractable sugars. And for example, one of the cases is the bioethanol production without pretreatment. Second generation biomass is, for example, includes lignocellulosic biomass, and it may also include agro-industrial residues or wood. And in this case, again, one example may be the production of bioethanol or biodiesel, but in this case, it needs a pretreatment because lignocellulosic materials are not so easily degradable, and we need a preliminary separation step then to produce the products that we want to generate. Third generation biomasses, in this case, is special crops, algae. This is also very popular nowadays, or plant residues. And now we can produce, with the combination of different processes, we can produce a range of potential products. I will go into the details later. And fourth generation biomass is the more, complicated to treat. This includes food waste, organic fraction of municipal solid waste, agro-industrial wastes, and we have here again complex processes, an array of different treatments, and the target is the generation of multiple products, both biomaterials and biofuels, and possibly or hopefully coupled with carbon sequestration options. Technical options for biorefineries, again, definitions of the terms that we are going to use. We can talk about platforms or products, feedstock, and processes that we can use in biorefineries. What is a platform? A platform is something that links or an intermediate step that links the feedstock and the desired product. So, for example, we can have the platform of C6 sugars, for example, simple sugars. And then from these sugars, we can generate different products. One example is, again, bioethanol. And you can see here that we have different options for platform. Another popular one in the, world of bio-waste is biogas. So then biogas may be used to generate different products. One may be, of course, methane, another one may be hydrogen. So again, as I told you before, a platform is something that links the input material to the final product. The products may be energy products, biodiesel, bioethanol, biomethane, or synthetic biofuels, and also energy in terms of electricity or heat. And also we may have, as I mentioned before, bioproducts, food, animal feed, fertilizers, or even more complex chemicals. The type of feedstock, I already mentioned this. We may have dedicated crops, or we may work with organic residues, for example, lignocellulosic residuals, or really waste materials. And again, we can use, we are going to use a combination of different processes, thermochemical processes, combustion gasification, hydrothermal treatment, pyrolysis, biochemical processes, both aerobic and anaerobic processes, chemical processes, this, as just examples, but of course, the range of chemical technologies that can be adapted is very large, and also some mechanical and physical processing of the material. This is also a concept that is becoming very popular, the concept of circular approaches. So we are now, this is not very easy to implement, but we are now trying, especially in Europe and also in the very highly developed countries, to shift from pyramids or from triangles to cycles. This is the very well-known hierarchical approach that is used in Europe, for example, for waste management. So we have here on top of the priorities given to waste management, we have the prevention of waste generation. Then, again, there's a microphone on. We have reuse options, recycling, other kinds of recovery, for example, energy recovery, and also at the final, at the last step, we have the final disposal of the waste. Moving to cycles, so to a circular approach, what we call a circular economy. Of course, we try to, get as much as possible from waste, and ideally without discarding any kind of secondary residue, let's say. Then probably this is actually not possible in reality, but we are trying to, make the process as circular as possible. What does this figure indicate? Basically, this is the traditional, circle for organic material. So we have biomass. We use biomass to grow, for example, crops. For example, we produce a range of materials that we can use for the production of food or plants. Then we have the consumption of food or green goods. And then we have that part of this food is discarded and becomes a waste. And we have this separate collection and we recycle the waste, for example, in terms of compost, again, to grow crops and to, start again this circle. Then the gray one is the circle concerning energy. So, for example, we may start from a bio-waste and generate biogas. Biogas may be used to produce a biofuel that is used in its turn to recover energy, so to produce energy. And again, we have a discard of a residue and we start in the cycle. And this purple circle is, what we call the circle of higher value materials. So we can think of using bio-waste or organic residues to produce high added value materials. So we use dedicated or sophisticated industry. We produce bio-based products, and at the end of their life, we discard the materials and we try to recycle as much as possible from this material and to reinsert them into the purple circle. Conversion steps in biorefinery, basically, conceptually, this is rather simple, not so simple to implement in terms of in actual processes to be applied, but in general terms, biorefinery starts from a selected feedstock. We may have a primary refinery. So, for example, including some pretreatments, some conditioning, and some separation of the individual components. We may have one or more platforms to generate intermediate products through different conversion processes. So this is the secondary refinery step. And then we have a third refining set of refining processes, and finally produce a range of materials or biofuels that are, can be marketed and can be used for different purposes. I see that the time is running very fast, so I'll skip this part. We may have different options in biorefineries. This is an example of a layout, a possible layout for algae. Just to mention that we have here different components of the material that need to be separated to generate a range of specific outputs. We may have a biorefinery dedicated to the exploitation of lignocellulosic biomasses. So you can see here that we have a large range of components that we can separate, around large range of platform, and also a wide range of potential products. When it comes to, the main topic of today's presentation, the bio-waste biorefinery, I've just reported one of the options because actually we have a big range of, potentially valuable or potentially reliable layouts. The ones that I'm now discussing are mainly based on AD, anaerobic digestion, so anaerobic processing of waste. So this is a general layout that I took from a paper that we have recently published in our group. We have a group within the IWWG, is the International Waste Working Group, and we have dedicated, working group or task group focused on biorefineries and more in general the management of organic waste. Of course, the group is open to new entries. So if you're interested, just email me and we can discuss if you can also provide a contribution to the activities of the group. So what we think we may apply to a bio-waste is, starting from this part, is the separation of the bio-waste in different components, typically carbohydrates and starch, which are more easily fermentable. We may have the cellulose and lignin fraction, the proteins, and also the lipids. And all these components may be subjected to different processes to, exploit the specific characteristics and composition. When we consider carbohydrates and starch, as I mentioned before, they usually are easily fermentable. So we may think of applying a fermentation, which is the first part, let's say, of anaerobic digestion. And in this case, we generate biogas. So we convert part of the organic fraction of the material into biogas, and also generate a digester that in general needs to be further treated. And you can see here that we have different options. The dashed lines represent alternative options. Of course, any type of, or every type of treatment opens a range of potential alternatives. So when it comes to biogas, we may think of having a chemical or thermochemical conversion of the biogas or some other type of upgrading. And we may be able to generate, for example, hydrogen, biomethane. Of course, we generate CO2, methanol, for example, ethanol, and other types of components of products, and also heat and electricity if we have direct use of the biogas generated. We may also think of having a biological conversion of biogas, so to exploit the potential for treatment of the biogas, and we may think of generating polydioxide alkanoates or polyhydroxybutyrates from the biogas and from a digestate as well. We also have the possibility of having thermal conversion of the biogas and to produce, for example, biochar and bio-oil, so they can also further be used for other industrial or environmental applications. Then what about the digestate? Digestate is, of course, composed of a liquid part and a solid part. So we may separate the two phases. So we have the liquid fraction that we can subject to chemical or biological conversion for the production of a number of valuable products, ethylene, again, polyhydroxide alkanoates, polylactic acid, biopropylene or biopolyethylene. Or we can think of directly using the liquid fraction for the production of a number of other products, ethanol, butanol, a number of volatile fatty acids, and so on. Then we have the other components. We have cellulose and lignin that we usually think they can be pretreated, for example, through hydrolysis, and again be directed to fermentation, or can be treated to produce a number of products, polymers, chelanes, carbon fibers, and so on. What about proteins? We may extract, for example, amino acids, animal feed ingredients, enzyme from proteins, collagens, and also other products, for example, to be used in pharmaceutical applications, and lipids through what we call the trans-esterification may generate biodiesel again, glycerol, or polyols. So you can see we have really a lot of options and a lot of potential for the exploitation of the original bio-waste. And I have to mention that more or less the technology for the conversion of each of these components into the final products already exist. In some cases, the technology is still at the development stage, or the transfer to the full-scale stage, but we already know processes that can convert these components into what I've mentioned here. Something more specific, starting from the previous scheme. This is something that is related to anaerobic digestion that is aimed to produce hydrogen, biohydrogen, and methane in a second stage. So in this case, the anaerobic process is maybe represented by dark fermentation. Dark fermentation is able to produce hydrogen as one of the components of the biogas, and also CO2. And of course, hydrogen is a highly valuable energy carrier, can be used directly in fuel cells, can be used in combustion processes, as a fuel for transportation, and also hydrogen has really numerous industrial uses. Or otherwise, we could think of using hydrogen and the CO2 generated in a second biological conversion to generate, for example, methane or other products. And of course, this may also represent a way to produce other components, for example, algae and cyanobacteria, to be used for other biological treatments. And more or less the rest of the layout is similar to the one that I have already described. Another option is to combine the dark fermentation stage with another kind of production of valuable products from the fermentate. So we have dark fermentation, again, production of a biogas which is composed by hydrogen and CO2, and the fermentate may be separated to isolate, for example, ethanol in some cases, or we may direct the fermentation process towards the production of volatile fatty acids. And these, of course, have value in themselves and may be used directly in different industrial uses, or may be used for energy generation purposes. And again, as before, the rest of the scheme is more or less similar. This is another option. The main target, or the first target, is just hydrogen. But in this case, we have two stages of hydrogen production. The first one may be, again, dark fermentation. You see here again, hydrogen and CO2. And we may also think to direct the fermentate that we obtain from this first stage to a second fermentation stage, in this case, photofermentation. And again, here we are able to generate biogas, which is mainly composed of hydrogen and CO2. Other options, fermentation with, again, dark fermentation with hydrogen production, and a second biological stage for the production of biopolymers, as I have mentioned before, typically polyhydroxy hydroxyalkanoids. The biological stage in this case may be either aerobic, probably it's more common, or anaerobic. And we have here the generation of an effluent, and we are able to extract the biopolymers that are accumulated in the biomass cells, and to produce these kinds of polymers to be used in a polymer industry. Another option, fermentation combined with electrochemical treatment. So again, what we obtain in terms of fermentation effluent, we can direct it to an electrochemical treatment, and we may think of producing electric energy using the electrons that are, generated in the reduction processes, oxidation reduction processes. So this is another option. So in this case, we directly produce electric energy from the process. We don't have an intermediate energy carrier in this case. Again, from the study that I've mentioned, this is just to have an idea of the yields that we expect for the selected processes that I have mentioned. So, for example, in terms of hydrogen production yield, these are data derived from different literature sources. So you see that we have considerable variation in the outputs, but on average, we can have something like 100 and 140 liters of hydrogen per kilogram of volatile solids of the original waste. In terms of methane, we are in a range between 400 and 500, more or less, liters of methane per kilogram, again, of volatile solids. And in terms of ethanol yields, you see 0.2, 0.25 grams of ethanol per gram of food waste. And biopolymers, really, again, very large variation ranges, but more or less 0.4, 0.6, 0.7 grams of biopolymers per gram of food waste treated. So we have already, as I mentioned before, processes on hand that may be, of course, further developed to increase the yield, to increase the reliability, to reduce the variation in efficiency. But of course, we have a good starting point for this, for the implementation of the schemes that I've shown before. Just a quick mention to combining biorefineries with CO2 sequestration purposes. We may also conceive biorefineries in a way that, along with the production of valuable biomaterials or biofuels, we also achieve some CO2 sequestration. And there are, of course, in addition to chemical sequestration options, we also have a range of biochemical processes that are able to sequester CO2. We have different kinds of microorganisms catalyzed by some specific enzymes that are able to produce sequestration of CO2 with even high efficiencies. And the advantage of biochemical processes applied for CO2 sequestration, we have this, very good feature, which is related to the fact that biological processes require milder operating conditions compared to other kinds of CO2 sequestration options. So it may be a good, good possibility to combine CO2 sequestration in biorefineries. We have different types of CO2 assimilating microorganisms. They may be both photosynthetic and non-photosynthetic, and also they can work under aerobic or anaerobic conditions. I will go fast on this part. And we can have also different, organisms that may be involved in the sequestration of CO2. One very popular is the use of algae for CO2 sequestration. And you see here, this is a very complex metabolism, but what I just wanted to show is the range of products that we may obtain by exploiting the algae metabolism, and also to stress then they need CO2 to operate for their metabolic purposes, for the metabolic reactions. So CO2 is one of the feedstock for algae cultivation, and we also at the same time produce a range of valuable products. Again, we produce hydrogen, we produce unsaturated fatty acids, we produce alcohols, we produce pigments, for example, chlorophyll, carotene, and so on, and we produce other types of valuable products, for example, hydrocarbons. Another example is mediated by bacteria. So in this case, we have photosynthetic bacteria, and again, they use up CO2 for their metabolic reactions. And even in this case, we have an input of CO2, and using different organic residues, we may produce a number of products. You see here sugars, bioalcohols, again, biopolymers, carboxylic acids, and hydrogen. Non-photosynthetic systems, they also be able to use CO2 for their metabolism, and again, producing a range of valuable products. Also, biological systems may be coupled, as I mentioned before, with electrochemical systems. And again, this is one example of how CO2 can be used with the aid of electrons generated by the electrochemical compartment to produce, using the microbial metabolism to produce a range of potentially valuable products. For example, you see here carboxylic acids, methane, hydrogen, or bioalcohols. Just to conclude, this is potentially applicable schemes for combining biorefineries with CO2 sequestration. So we start from this side, from the green part. We have photosynthetic systems, for example, algae, with an input of CO2. We use algae to produce number of products, and we have, of course, a residue, the oiled algal cake, that we can feed to, for example, fermentation system. In this case, we can use different sources of carbon, of inorganic carbon, bicarbonate, carbonates, or even CO2 as a buffer for the biological system, because usually fermentation generates acids, and these acids cause pH to drop. So if we use carbonate or bicarbonate of CO2, we may be able to buffer the system. We feed organic residues into the fermentation system, and we generate, for example, biogas, so biomethane, hydrogen. We generate alcohols that have a value in themselves, and also carboxylic acid. The residual organic fermentate can be fed, as I described it before, to a photofermentation system. Again, photofermentation systems use up CO2, they take up CO2, and we generate here biohydrogen and biopolymers, and the effluent from the organic effluent from the fermentation the photo fermentation system, sorry, can be fed to a bioelectrochemical system, again fed also with CO2, and we may be able to generate methane and other organic products for different industrial uses. And what we have here as a residue, we may feed again to the photosynthetic system. So this is basically an example of how, in a relatively simple layout, we may combine the different needs to produce valuable materials and to sequester CO2. So, going to the conclusions or to the final considerations, of course, we have the potential to develop biorefineries for the exploitation of bio-waste or organic residues. But of course, we have still several challenges to take into account. For example, we have to take into account that waste materials or organic residues can vary, can fluctuate in quality, or can vary in production depending on the season. Also, we have some feedstock which have low purity. So this is an issue when we want to produce high purity outputs. We should understand how to combine different feedstock material in order to maximize the yield of production of the final materials and to maximize also the quality. Of course, we have to develop new technologies or to refine the existing ones to increase the yields, to increase the environmental profile of the processes, to improve the reliability or to, the maintenance of steady state conditions. There is also an issue related to the optimal size of biorefineries, because we may think of two different extremes for biorefineries. We may think of high performance multi-feedstock installations, big plants with multiple processes, or we may choose lower or smaller installations, decentralized production, for example, of dedicated bioproducts or biofuels in more specialized systems. So, a lower range of products and, of course, a lower range of processes to be applied. So, relatively simpler systems. Another issue is related to the market demands, to the fluctuation of market needs, and also the different, the variability of the price of market price of products. And another challenge is how to integrate biorefineries with other industries to, for example, improve the circulation of materials and energy to attain the objective of more rational use of natural sources and also of residual materials. And also, this is very important, we have to assess the risk for potential spreading or recycling of impurities and contaminants that may be associated to waste materials. So, just to conclude my presentation, in order to, to boost the implementation of biorefineries, we, of course, need policies and initiatives that may allow, the application of these new technologies, especially to waste materials. To do this, we, of course, need to be sure about the fluxes of materials, the flows of materials, and the biofuels that we generate. So we need to draw materials and energy balances And doing this, we have to base on reliable data. So we need reliable data related to the performance of the different processes. And of course, this is a prerequisite for the assessment of the feasibility of different technological implementations of biorefineries. We need systematic quantification of both the direct and indirect emissions from the processes, and also the savings, for example, in terms of saving in greenhouse gas emissions that we generate using residual materials instead of natural resources. And we also need to assess the implications that we generate on other compartments, the sources of scarce materials, the consumption of water, the use of land, the production of other kinds of residues that probably will be more concentrated in undesired components or contaminants. And also we need to boost a synergistic integration of different processes. So in terms of what we call industrial symbiosis. So these, of course, are very wide subjects that include not only technical aspects, but they include also policies for waste management and in general for industrial production, and also strategies at a very broad scale, for example, for the mitigation of greenhouse gas emissions. So more or less, this is what I was I was expecting to tell you about the implementation of biorefineries. I hope that the presentation was clear enough and stimulating further discussion. So thank you for listening, and I'm open to questions.
Yeah, thank you so much for your very comprehensive, highly informative presentation. So really, amazing presentation. So now everyone should be understanding the importance of biorefineries, because we have to address these organic waste, and also, need for conserving resources and creating products out of this bio waste. And you have nicely summarized all kinds of opportunities, technologies, and different ways that this could be done. So I am really excited. I think this aspect is going to receive more attention as we go into the future, to convert the bio waste into valuable products. And also, as you mentioned, CO2 sequestration can be accomplished with these things. So you can get a lot of benefits out of these things. And as engineers, there may be some geotech engineers. There was a question on geotechnical, these days we are using a lot of these new technologies for for example, ground improvement. We use materials like polymers, enzymes, biochar, compost, chelants, carbon fibers, and all those things. So I'm just saying, because some of the attendees may think, how could I be involved in these kind of projects? We have to promote these kind of projects because the end products could be used in our field, right? So that's the more motivation for us, because a lot of times we use some materials, and if they're expensive, nobody wants to use it. So I think that I really enjoyed it. I learned a lot of new stuff from your presentation. So I greatly appreciate making an excellent presentation. So you may want to see the chat box and see some technical questions you want to answer. Yeah, please.
Yeah, there were a lot of questions, and I don't know where to start from.